Thank you, Chairman. I'm Shohei Imai from Nata in Japan. I'm honored to stand here and talk to famous professor and researcher about these topics. Our company is basis of passive components, whereas today I want you to know about our technology about handset power amplifier at FR1. Here is today's outline. At the beginning, we will discuss the handset PA requirements. Next, load variation problem, which is a bottleneck of DPA for handset. The concept of dual adaptive bias DAB is introduced. We will discuss the monitoring circuit, which is a part of DAB. The fabricated DPA in a single gallium arsenide chip are presented. Some measurement result of the DPA with 5G NR signal at 2.5 GHz are presented. Finally, I will conclude with a comparison with other techniques. In recent handset, since high PA signal are used, the development of technology to increase efficiency in backoff is very active. As one of those techniques, Doherty power amplifier, DPA, is one of strong candidates. The DPA is composed of a carrier amplifier and a peak amplifier. High efficiency at backoff can be realized because the peak amplifier outputs only when a large power is input, and turns off when the power level is backoff. There are some schemes for switching turn off and on of peak amplifier. One scheme uses a detection circuit to control a bias point according to the input signal. This scheme is referred as conventional adaptive bias, CAB, for contrast to our proposed scheme. The CAB may be able to operate without DPD because the distortion is not so significant. However, since the antenna environment changes in the handset, it is necessary to consider the situation of load variation. In this situation, CAB techniques must be improved by other techniques because it causes significant distortion. In contrast, our target is a technique that achieves high performance at each condition without DPD. Before introducing our techniques, I introduce other techniques for improving robustness. These are references for techniques that improve the load variation robustness of DPA, not only for handsets. These require various additional tech components. The 19-degree hybrid combiner is not preferred for handset at low frequency such as FR1 because it is relatively large components. Supply modulator is also large and expensive. A compact impedance monitor is challenging, and high-speed operation adapted to a broadband signal is also challenging. This study focused on a compact system suitable for FR1 handsets that handle broadband signals. Next, the load variation problem is discussed in two steps. First, before discussing the problem, we confirm the behavior of CAB as nominal load. A detector is placed in the conventional adaptive bias to control activation of peak amplifier. The detector adapts to the input signal to control the bias of peak amplifier. Then the output current from the peak amplifier increases in large input power region. Whereas the output current cannot increase as rapidly as the ideal curve. The output current is often insufficient. The load of carrier amplifier is nominal load at small input. When the input power is large, the load of carrier amplifier decreases. This decreasing is achieved by the peak amplifier current flowing into the combiner. This behavior is called as load modulation, and is the feature of the special combiner for DPA. The load decreasing is also insufficient in CAV because of the shortage of output current from the peak amplifier. As finally, the high load impedance introduces high voltage amplitude of the carry amplifier. This high voltage often exceeds the maximum, and the carrier amplifier operates in overdrive. The time domain behavior of the carrier amplifier in the overdrive state is depicted. The output voltage of the carrier amplifier is sinking. In the ideal state, the minimum value is above the knee voltage and no distortion occurs. On the other hand, the voltage amplitude enlarges in CAV. The swing bottom voltage is clipped by the knee voltage. When the output voltage waveform is clipped, it becomes nonlinear and generates distortion. When the significant clipping is occurred, digital pre-distortion technique is required. The problem of load variation in CAV is discussed. We consider the situation where the load of carrier amplifier becomes high impedance by the reflected wave from the antenna of the handset. This condition is a bad scenario for CAV, as shown in the figure below. The output current from the peak amplifier is not changed in the CAV because the CAV does not include feedback control. Whereas the load of carrier amplifier is increased in all range of input power by reflected wave from the antenna. The high load increase voltage amplitude of carrier amplifier. Voltage creeping occurs from a small input region, and creeping would never be accepted. The concept of dual adaptive bias is introduced. As first, its configuration. This is a block diagram of proposed DAV. In DAV, in addition to the CAV circuit, a drive level detector, DLD, for monitoring the drive level of the carrier amplifier is placed. The drive level means how close the bottom of swing voltage to knee voltage. Its details will be introduced after the DAV behavior is explained. The drive level signal is used as gain control signal of the VGA. The VGA controls the input signal of the detector. The detector converts its input power to the peak amplifier bias point. It controls the bias from class C to class A according to its input power. The detailed configuration of the VGA and the detector is not explained in this presentation. If you are interested, it will be explained in our extended paper currently under review. Next, the behavior when the load variation occurs will be explained. It's focusing on the state where the input power is small. At low impedance, the voltage amplitude of carrier amplifier is small. Then the DOD outputs load level. In this case, the gain of VGA is controlled as low, and the input signal of the detector is small. The signal is not sufficient to drive the detector, and the peak amplifier biased as class C. On the other hand, the behavior when the impedance of carrier amplifier increases will be described. Even if the input power is small, the voltage amplitude of carrier amplifier increased, and it may be clipped by knee voltage. In that case, the DLD outputs high drive level, and the gain of VGA is controlled and high. As a result, the peak amplifier are biased as class AB and activated. In class AB bias, peak amplifier has sufficient gain, and it outputs large output current. As finally, the load of carrier amplifier is decreased by the load modulation through the combiner. The activation of peak amplifier is enhanced until the drive level is reduced to a suitable level. This behavior is feedback control. Additionally, the feedback control of DAV also improves the performance in nominal load. As first, this is conventional adaptive bias behavior at nominal load. In the CAV, at large input power, the input signal of the detector is also large. The large input signal drives the detector and the peak amplifier bias to class AB. As previously mentioned, the peak amplifier bias point is often insufficient because sharp activation of peak amplifier is difficult. Therefore, the load modulation through the combiner is also insufficient. As a result, carrier output voltage is in overdrive and generated distortion. On the other hand, the behavior is improved in the DAV. In contrast, the DLD detects high drive level of the carrier amplifier in DAV. The high drive level is used as gain control signal of VGA. The gain of VGA is increased. The input signal of detector is also increased. The additional increased detector input power is sufficient to drive the detector. The detector controls the peak amplifier bias up to class A. The peak amplifier bias increasing reduces the drive level via load modulation at the combiner. As finally, the peak amplifier bias is increased until the carrier amplifier drive level is reduced to proper level. This is the benefit of feedback control. The features of this configuration are glanced. Adapting to the input signal and controlling the bias of peak amplifier is the feed-forward control. Since the feed-forward control does not include the DLD in the path, it can operate at high speed. On the other hand, adapting to the drive level signal and controlling the bias of the peak amplifier is a feedback control. This control can increase the robustness against the load variation. By making controlling adapting in dual way like this, the bandwidth of 100 MHz and load variation tolerance are achieved. The detail of drive level detector is explained. This is a configuration of the drive level detector, DLD. The final stage of carrier amplifier are configured differentially with gallium arsenide HBT. The gallium arsenide HBT has good at high power density at this frequency and commonly used. The differential configuration is selected for low loss and wideband characteristics in the combiner. Then the DLD is also configured differentially with gallium arsenide HBT. The DLD inputs are connected to the output of carrier amplifier directly to monitor drive level. And the drive levels are output from here. The DLD consists of 3 components: a comparator, an amplifier, and a rectifier. The figure on the right illustrates the time domain behavior at high drive levels. As previously mentioned, the knee voltage creeping occurs at swing bottom voltage. Then the DLD configured to monitor swing bottom voltage. A comparator is achieved by the diode character between base and collector of the HBT. The base is biased so that current flows when the swing bottom voltage becomes lower than the threshold voltage. The threshold voltage is set to voltage slightly higher than the knee voltage and detected before knee creeping occurs. During the duration of the voltage being lower than the threshold voltage, base current flows from the transistor's base to its collector. The sink current at the output port is too small to smooth and detect in a short time. Therefore, amplifying at the post-stage is required. The gain of post-stage amplifier must be sufficient to achieve quick response. The amplifier is designed as two-stage amplifier to meet the high gain requirements. As finally, the amplifier differential signal drives the rectifier. The differential drive doubles the rectifier current in one cycle and makes the response fast. Then differential configuration at DOD would be suited for our situation. And a few nanoseconds response time is achieved. Fabrication. As a proof of concept for DAV, we have integrated it with our previous studied DPA. The structure of the combiner and final stage in the DPA is same as in our previous study. The DPA is configured 3 stages. All stages of peak amplifier are controlled by the DAV. The DPA with DAV expect for the combiner is fabricated on a single gallium arsenide HBT chip. The overall chip size is 1.25 mm times 1.3 mm. As shown in the right figure, the area of the components for the DAV consists of a BGA, a detector, and a DOD is about 10% of the total chip size. Measurement results. Some measurement results are now displayed. All of them include 2 circuit configurations. One is introduced DAV with red line. Another is conventional adaptive bias as CAV with gray line. The conventional type is measured under cutting of the input power of the input of the DOD. The character is tested in 100 MHz bandwidth 5G signal without DPD assistant at nominal load. ACLR is maintained as lower by applying the DAV. 42.8% of PAE is obtained with minus 35 dBc ACLR. EVM is also measured and shown in the right figure. The EVM is also linearized by applying the DAV. The modulation signal measurement was also performed at VSWR equal to 2. The graph summarizes the measured ACLR and PAE at 31.5 dBm output power. The DAV reduced ACLR below minus 30 dBc of the 3GPP regulation under any reflection phase with few % degradation of PAE. The ACLR frequency response is also improved by the DAV. This and other robustness improvements will be discussed in an extended paper currently under review. Conclusion. I will conclude this presentation with comparison table. This table is summary of recently reported DPA with robustness for the load variations. Other reported techniques require some components, such as hybrid combiner, supply modulator, or DPD, or impedance sensing system. These components are not required in our technique. Our technique requires a dry level detector, which is compact and easy to integrate in single gallium arsenide, a single chip. Despite such simple structure, its fast response achieved signal bandwidth of 100 MHz. The bandwidth is 4% of the carrier frequency, and this is high performance. Then we believe this technique is very suited for low-band handset Doherty power amplifier. Thank you for your attention.